problems on finite element analysis, I want to discuss some of the problems what we face. For example, here the first problem is calculate the element stresses sigma x, sigma y, tau I xy, sigma 1, sigma 2 and the principal stresses and strains with the angles. CST means constant strain triangle. Element is shown x-axis, y-axis. 1, 2, 3 are the vertices of the triangle. 10, 8, 15, 5, 18, 12. These are the coordinates. But in the question itself, he has given nodal displacements. Nodal displacements are what? Minus 2 mu m means micron meter. 1.0, 0.5, 1.5, 1.2, 2.8, all these are given, mean these are the nodal displacements at each node, means each node will move by the so small displacements. So, and here the Young's modulus is given, mu is given, and assume plane stress condition. It means first the given data you please enter. I am showing you, and enter all these nodal coordinates x1, x2, 18 mm, x3, y1, y2 and the nodal displacements all are in 2.0 mu m means 0.002 mm. Everything you please convert it to millimeters. Now what is to be done? After converting all to mm, Young's modulus you convert it to GPa to Newton per mm square. Mu is 0.25. For a given CST element, the element stresses are given by C. Stress is what is this? Young's modulus is stress by strain, so stress is Young's modulus into epsilon, but that Young's modulus is for 1D. We call it as D matrix, and here, therefore, sigma is dBu for the plane stress conditions, and using the constitutive matrix, D is a standard matrix, E divided by 1 minus of mu square, E divided by 1 minus of mu square, 1 mu 0 mu 1 0 0 0 1 minus mu by 2. Put all the values, you get this matrix, and now simplify this, you get 56 into 10 to the power 5 410 140 like this. The strain displacement matrix is a standard matrix. There is a proof of this. Students have to remember this, and area of the triangle is given by half of 1 1 1 x1 all the coordinates y1 y2 y3 x1 x2 x3. Put the values, simplify, you are getting 22 mm square, and now you are also getting the coordinates here. What is that? Beta 1 beta 2 beta 3, that is y1 y2 minus y1 s minus of 12, that is your 5 minus of 12, 12 minus of 8, 8 minus of 5, 18 minus of 5, so that you are getting all the values. Next step, you please put it in the form of what? Matrix, that is your strain matrix, and it's a 1 over all the substitutions, that's all. And here therefore u is already given in the question itself. Put all the values in the column matrix, you get it. Equation 3 and 4 you have understood. Substitute all this, you get sigma x, sigma y, tau xy, stress along x, stress along y, and shear stress. You substitute all this. See, the sizes are very important. 1 is 6 by 1, 3 by 6, 3 by 3. Simplify, which you have to practice it. When you simplify, the answer will be a 3 by, see here all I have simplified, so that you get the final answer 14 by 11 into this. Now same type, if you go to problem number 2, for a 4-noded rectangular element shown in figure, please determine the following: Jacobian matrix, strain displacement, element strains, element stresses. Young's modulus is given, mu is given, zeta and eta are the coordinates, it is 0 0. U is given, displacement. Assume plane stress condition. It's almost same type. Go on saying, we are putting the Jacobian matrix. Where is this one? J11, J12, J21, J23, and the formula for that using the shape functions and your eta and zeta. Then substitute it in the nodal displacements. You get Jacobian matrix. Name of the scientist is a Jacobian. He has told this method. and it is 1.5, 0, 0 and 1. That is very important. What is the use of Jacobian means? Well, if you take the value of the Jacobian is the determinant of this. So if you take the determinant of Jacobian is how much? 1.5 into 1 minus of 0 into 0. So the answer is 1.5. It means it can stretch by 1.5 times the actual dimensions. To find the strain displacement matrix, we know the strain displacement matrix is a standard one using Jacobian. Substitute all the values, you will get 1.5. That's what. So this is the method. Now B matrix you are getting, the B matrix you are getting here and here. This is the nodal element matrices epsilon, and this is the find the element stresses sigma d epsilon, where d is stress strain relationship. Always this is standard one. You see this, and you are going to get the element. Now the element stresses, element strains, element stresses Newton per cm square. Means Jacobian matrix is this. Jacobian value is 1.5. Strain displacement matrix is what? 1, 2, 3, 4, 5, 6, 7, 8. It is what? 3 rows, 3 by 3 rows and 8 columns. Element strains are 3 and your element stresses are 3 Newton per cm square.